Good afternoon, our respected organizers, session chairs, researchers, academicians, industry professionals, and dear friends. I'm Engineer Aditya Singh, ISDS M.ASE AMIE. I've been an independent researcher, editorial review board member in 6 American international journals, reviewer in 10 American international journals, 6 Singaporean, 1 Indonesian, one Swiss-based international journals, as well as alumni mentor registered by Amrita University alumni, Amrita Vishwavidyapeetham, India, think tank expert, Beijing Zhongzuan Electric Power Energy Big Data Research Institute at present, as well as ex-research mentor at Academy Nova World, Kalipur, India, and ex-alumni mentor LPU. Today's topic is the need of lifecycle management in sustainable infrastructure requiring governance framework, especially for digital twins led by AI. Outline in today's presentation, introduction, literature review and research gaps, and other topics will be covered. Introduction, general. Infrastructure systems are becoming increasingly complex due to urbanization, climate change, aging assets, and growing societal expectations for sustainability and resilience. Traditional infrastructure management approaches, which rely on periodic inspections and reactive maintenance, are proving inadequate for these evolving challenges. Recent advances in AI digital twins, IoT and cloud computing are transforming how infrastructure assets are planned, monitored, operated, and maintained. However, it has been found that technological innovations alone are insufficient. So, effective life cycle management also requires governance frameworks which make sure that transparency, interoperability, accountability, cybersecurity, and long-term institutional capability are also present. Background: the concept of sustainable infrastructure has expanded considerably during the past decade. So it has been found that infrastructure management focused primarily on construction quality and initial capital investment. Today, infrastructure is expected to remain safe, resilient, resource efficient, and environmentally sustainable throughout operational lifetimes that often exceed 50 or even 100 years, and more in the case of monumental structures. International studies increasingly emphasize life cycle thinking because most of infrastructure costs, environmental impacts occur after construction, during operation, maintenance, rehabilitation, eventual decommissioning. Digital twins have emerged as an important technological innovation because they continuously synchronize physical infrastructure with virtual models using real-time operational information. And AI further strengthens digital twins by enabling predictive maintenance, anomaly detection, performance forecasting, and intelligent decision support. Literature review and research gaps, roughly 45 published papers uh, where the recently published one were taken into consideration, and numerous gaps which included uh, relatively few governance frameworks which have been specifically developed for AI-enabled lifecycle management. Then standardized maturity models for evaluating organizational readiness are still limited, and the existing studies mostly emphasize technological development while providing comparatively less attention to governance, institutional capacity, and interdisciplinary collaboration. Then empirical evidence from developing economies remains relatively limited. Plus, digital twins, life cycle sustainability assessment, resilience planning, circular economy principles, and climate adaptation uh, must be integrated properly. So, uh, the relevance of this study: infrastructure systems worldwide are increasingly affected by aging assets, climate change, urbanization, and growing sustainability expectations. So this study will connect lifecycle asset management with AI-enabled digital twins and demonstrate why governance is fundamental to digital twin implementation. Plus, it will extend existing digital twin research by incorporating organizational readiness and support sustainable infrastructure management through integrated governance frameworks. Infrastructure lifecycle management. Uh, it should the infrastructure should be managed as a continuous life cycle rather than as isolated construction projects. So life cycle begins with strategic planning, feasibility analysis where future infrastructure demand, infrastructure conditions, and economic feasibility are evaluated. So at different life cycle stages, like during design phase, these requirements into engineering solutions while considering resilience, sustainability, and maintainability. Then construction represents only one stage within the broader life cycle. After commissioning, infrastructure enters its longest phase, which is operation and maintenance, and infrastructure performance globally changes because of aging, environmental exposure, traffic loading, and material deterioration. Then periodic rehabilitation extends service life, while eventual renewal or decommissioning concludes the life cycle. Then life cycle management integrates information from every stage to support informed decisions regarding maintenance scheduling, resource allocation, investment planning, and sustainability assessment. Then why traditional life cycle management is insufficient. Despite advances in engineering practice, many infrastructure organizations continue relying on reactive management strategies as infrastructure inspections are frequently conducted at fixed intervals rather than according to actual asset condition. And information is often dispersed across multiple independent databases, limiting comprehensive asset management. Then climate change further complicates infrastructure management because historical design assumptions may no longer represent future environmental conditions, and engineering decisions may therefore rely on incomplete, outdated, or inconsistent information. Digital twins across the life cycle, infrastructure life cycle. Digital twins are virtually representations of physical infrastructure that remain continuously synchronized with real-world conditions through data collected from sensors, operational systems, and engineering models. So, unlike static digital models, Uh, Digital twins continuously evolve throughout the infrastructure lifecycle, uh, particularly during the planning stage. They enable engineers to evaluate alternative scenarios before physical construction begins. Then, during design, the digital twins support optimization of structural performance and sustainability. Then, in the construction phase, they facilitate progress monitoring and quality management. And during the operation, they integrate sensor information with engineering models to evaluate infrastructure condition non-stop. And AI analysis says these data streams to predict deterioration, identify anomalies, estimate remaining service life, and recommend maintenance interventions. So, through this, it could be said that the reactive maintenance is possible at the right time before the failure happens or deterioration increases. Then artificial intelligence at the intelligence layer, uh, AI provides an analytical capability that transforms digital twins into intelligent decision support systems. ML algorithms identify complex patterns within operational data sets. Then deep learning enhances uh, image interpretation, supporting automated damage detection from inspection, photographs, or drone imagery. Then there's computer vision, which improves quality control and structural inspection by automatically identifying cracks, corrosion, deformation, and construction defects. Then natural language processing assists organizations in analyzing inspection reports, maintenance records, and technical documentation. Then predictive analytics forecast equipment failures before operational disruption occurs. So reinforcement learning can optimize maintenance scheduling and operation control under changing environmental conditions. Integration of emerging digital technologies. Digital twins achieve their greatest value when integrated with complementary digital technologies, which includes BIM, which provides structured engineering information describing infrastructure geometry, materials, and design specifications. Similarly, IoT, which continuously monitors structure behavior, environmental conditions, traffic loading, vibration, and operation performance. Then GIS, cloud computing, big data platforms, and digital support systems. Together, these technologies create a comprehensive digital ecosystem supporting lifecycle infrastructure governance. Methodology. The recent year published papers were taken into account, which are governance framework essential for lifecycle management in the context of sustainable infrastructure. And uh, case studies like Europe, Singapore, and Portugal were taken into consideration. And such international case studies were connected to sustainable infrastructure with lifecycle management requiring governance framework. Then sustainability benefits uh, of AI-enabled lifecycle management. So sustainability is generally evaluated through three interconnected dimensions: environmental, economic, and social performance. And modern infrastructure management must optimize all three simultaneously rather than treating them independently. From an environmental perspective, AI-enabled digital twins improve energy efficiency, reduce unnecessary material consumption, optimize maintenance interventions, and help lower greenhouse gas emissions throughout an asset's operational life. Economically, life cycle management minimizes whole life costs instead of focusing solely on initial construction expenditure. Socially, continuous monitoring improves public safety by identifying deterioration before failure occurs. Uh, why governance frameworks are necessary? Governance defines how infrastructure data are collected, validated, shared, protected, interpreted, and used for decision making. So, it is necessary that data remains transparent, used ethically, and accountability of how it is being used and who should be accountable. Then interpretable and human-centered. The human oversight should be there, and the data collection, which is necessary in cyber, uh, in these type of infrastructures which are interconnected through such advanced technologies. So the important data must be secured, and then explainable uh, facility should also be there. Then proposed governance framework for AI-led digital twins. The first layer is data governance, ensuring high-quality, interoperable, secure, and standardized infrastructure information. Then the second layer is AI governance, focusing on model validation, explainability, transparency, algorithm monitoring, risk assessment, and ethical oversight. Then the third layer is digital twin governance, which defines responsibility for maintaining synchronized virtual representation, validating sensor information, and ensuring lifecycle consistency. Then in the fourth layer, infrastructure governance, integrating digital twins into asset management, maintenance planning, resilience assessment, sustainability evaluation, and investment decision making. And the fifth layer is national and international governance, which establishes legal frameworks, technical standards, procurement regulations, cybersecurity requirements, and uh, international interoperability principles. Supporting all governance layers are cybersecurity stakeholder participation, continuous auditing, regulatory compliance, and institutional learning. Rather than operating independently, these governance layers interact continuously throughout the infrastructure lifecycle. Organizational readiness. Even the most sophisticated digital twin cannot deliver value unless organizations possess sufficient readiness to implement it. Therefore, the leadership readiness, which involves executive commitment, a strategic vision, and long-term investment in digital transformation. Then, similarly, technological, uh, human readiness, governance readiness, financial readiness, and ecosystem readiness must also be considered as organizational readiness strongly influence successful digital twin implementation. So if we are ignoring any one of them, then the proper outcomes could not be attained. Case studies. Singapore provides one of the most mature examples of digital twin implementation within urban infrastructure, facing limited land availability, high urban density, and ambitious sustainability objectives, Singapore developed the Virtual Singapore Initiative. This platform integrates BIM, GIS, AI, IoT sensors, and cloud computing into a comprehensive 3D digital representation of the city. Singapore, therefore, illustrates that technological innovation and institutional governance must evolve together to achieve sustainable infrastructure management. Then, the case of this one, Portugal, uh, climate change has increased flood risk across many European cities, creating significant challenges for infrastructure management. And Lisbon has adopted digital twin technologies supported by AI to strengthen flood resilience and climate adaptation. The system integrates hydraulic models, environmental monitoring, sensor information, and predictive analytics to simulate flood scenarios before extreme events occur. The case demonstrates that life cycle management extends beyond maintenance activity to include long-term climate adaptation and resilience planning. Then Europe, digital twins for building operations. Many European research projects have investigated digital twins for operational stage buildings rather than concentrating exclusively on design and construction. These initiatives focus on improving operational performance throughout the building life cycle. So AI intelligence analysis um, operational information to identify inefficiencies, predict equipment failures, and recommend maintenance interventions. So, successful operational digital twin requires organizational commitment to standardized lifecycle information management rather than isolated technological implementation. Results and discussion. Growth of sustainable infrastructure worldwide in Figure 1 could be seen, and the market value in the year 2024 was 58 billion point five point five US billion dollars, and in the year 2034, in the span of 10 years, uh, it is expected to grow about 8 times. So the market of sustainable infrastructure will be uh, growing significantly in the coming 8 years. Uh, so it is necessary to focus on the life cycle management and the governance readiness aspect, so that the sustainable infrastructure uh, could flourish properly and give fruitful outcomes, which could meet growing demands uh, of the present as well as future generations. And growth of digital twin market in the year 2025, it is expected, it was calculated at 21 0.14 billion US dollars, the market value, but in the span of 5 years, it is expected to go uh, almost 7 times, which is a significant rise in the value of digital twin market. So it could be said that the digital twin technologies will be invested more in the coming 4 years, and their incorporation in sustainable infrastructure will increase. So the governance readiness should also be considered, and AI analytics as well as other technologies which could be integrated properly. Then policy recommendations. Uh, The government should establish national digital twin strategies supported by interoperability standards, cybersecurity frameworks, and lifecycle oriented infrastructure policies. Then infrastructure owners should integrate digital twins with long-term asset management rather than limiting implementation to individual projects. Uh, then industry-wise digital infrastructure workforce deployment, development, and governance capability as well as organizational change management must be focused simultaneously and academic institutions should strengthen interdisciplinary education, combining civil engineering, artificial intelligence, data science, and infrastructure governance more in the coming years. And professional engineering organizations should develop certification frameworks and technical guidance supporting trustworthy implementation of AI-enabled digital twins. Conclusion: the life cycle management in the case of sustainable infrastructure and how governance frameworks are essential were highlighted in this study. Then global case studies like Lisbon, Portugal, Singapore, and European case studies were taken into account. And through the studies, the several existing gaps were overcome, and the uh, governance framework uh, were explained, as well as the future scope of sustainable infrastructure with a governance framework, uh, including life cycle management, were explored. Thank you.